Operations with matrices. Here we talk about the very basic operations when it comes to matrices. What does it mean for matrices to be equal? What can you do with equal matrices? Well, you can do a whole lot. Also, in terms of adding, subtracting, multiplying matrices, these are just basic operations concerning matrix algebra. And then from there, we introduce the trace of a matrix, and we look at what that means. Later on, we talk about the transpose and how important that is to symmetric, skew symmetric matrices, and several other applications of the matrix. Lastly, we deal a little bit with just going back to the previous work in solving a system, solving a matrix. Here, nothing new, but we will introduce new ideas when it comes to multiplying matrices. We can multiply a matrix by a number. You can multiply a matrix by another matrix, but we have to do that with respect to the size or the sizes of the matrices. So first, equal matrices. Definition: a matrix is defined as a rectangular array of numbers denoted always by capital A, and here in parentheses with the IJ entries. Here I represents the row and J represents the column. The size of a matrix is important. The size of a matrix is denoted by here the matrix A, M by N, where M represents the number of rows, and then N represents the number of columns. So here, notice that we have, in terms of uh, uh, the number of the rows, there are M rows, and then there are N columns. Seems like the first time when I grab this pen, just for the first time, it wants to act funny. So we have the number of columns, there are N, and then the number of rows, M. We say that two matrices are equal if they have the same size, and if each corresponding entries are the same. Otherwise, the matrices are not equal. Let's see. We look at the first example. Look at these two matrices, A and B. Well, this is cosine of 0. Cosine of 0 is 1, so those entries would be 1, 2, 3, 4. So the matrices are the same size. It's a 2 by 2, and this is also a 2 by 2. And then each corresponding entry matches up, so they're equal. Now for the next two matrices, they have the right same size, 2 by 2, and what's in them looks to be about the same, but they don't correspond. See here, one is not equal to 4, and then likewise, and then with all the other entries. So for two matrices to be equal, they must have the same size, and each corresponding uh, entry must be the same. Now for matrix here, A and B, they have different sizes. This one is a 2 by 3, 2 rows, and then 3 columns. And then matrix B is a 3 by 2. So they have different sizes. Doesn't matter about what's inside of them. They don't correspond because they're not the same size, even though the number of combinations seem to be the same. But it's the position and the size that's equally important as well. And we talk about adding and subtracting matrices. You can only add or subtract matrices, one, if they have the same size, right? So that's first and foremost. They got to have the same size, and then to add or subtract, you are only uh, adding or subtracting the corresponding entries. So for the first example, that the matrices are the same size, so we can add 2 plus 4, 6, 1 plus 3, 4, 5 plus 0, 6, and then 5 plus 2 is 7. Now, the next example, these pairs, we cannot add because they have different sizes. This is a 2 by 2, and this is a 2 by 3. Now, multiplying matrices, it's a little bit more involved here. Um, Multiplying two matrices, we must first consider, I think, as an introduction, the dot or the inner product. Um, the, the inner product of two matrices, you recall, and just another phrase for that may be the dot product. You remember that. If we have two vectors, let's say u and v, and here u and v come out of the third space, the Euclidean third space. They have three tuple vectors. So when we do the dot product of u and v, it just becomes u sub 1 times v sub 1 plus u sub 2 times v sub 2, and then plus u sub 3 times v sub 3. So after the dot product, that result is just a scalar, right? So the dot product is no more a vector. Its result just gives you a number. So as an example, if we have these two vectors, u and v, and just find the dot product, so it becomes 2 times 3 plus negative 3 times 1 plus 4 times negative 2. So it gives us 6 minus 3 minus 8, and so that gives us negative 5. Now you keep that in mind because we used that idea of multiplying matrices. We used the dot product concept. So to multiply the matrices, one, the order must be correct. What do we mean by that? You can only multiply matrices of the following format. Here, the matrix A, the matrix B. Remember that this is A is the M by P. That means it has M rows and P columns. Matrix B has P rows and N columns. Now, what does that mean? In order to multiply matrices, the number of columns for A has to be the same as the number of rows for B, which leaves then, if that's the case, the resulting matrix would be an M by N matrix. So here the resultant matrix, its row comes from the first matrix A, and the resultant matrix C, its column comes from the number of columns from the second matrix B. So you got to make sure that that's the case. If not, then you say that matrix multiplication is impossible. Number two, each ij entry of the resulting product is the dot product of the ith row of the first matrix times the jth column of the second matrix. So you just think to multiply matrices, all you're doing is just multiplying a row from the first matrix times the column of the second matrix. Just think row times column, row times column. Don't fall in the ditch, because if you fall in the ditch, you'll come up saying column times column, or column times row, or or some other weird algorithm. And back where I'm from in the country, we do a whole lot of falling in the ditch. But anyway, um, let's look here, find the product of these matrices. And what I did was to put the answer over there, not for you, but for me, because my mind kind of goes crazy. Let's check the size. So this is a 3 by 2, and this matrix here is a 2 by 2. So those numbers there must be the same. Got it. So the resulting matrix has to be of this size, a 3 by 2. So the resultant matrix will look like that first matrix. So we're thinking here, this is going to be uh, this first row times this first column. That'll be that first entry. So I guess I could circle it. So it's the dot product of these two guys. So that's 3 times 4 is 12, plus 0 times 0, that's 0. So we get 12 plus 0 is 0. I'm going to go straight across. So again, it's the first matrix, the first row of the first matrix times here the second column over here. Now, if you think, let's get the rows. This is row 1, row 2, row 3. This is column 1, this is column 2. And then row 1, row 2, row 3, column 1, column 2. So each uh, entry in here has to match up, right? So this is R1, C1, R1, C2, R2, C1, R2, C2, R3, C1, and then R3, C2. So we got 12 for that first one. So now we do R1, C2. So that's negative 3 minus 0 is negative 3. Now R2, C1, row 2, column 1. So that's negative 1 times 4 is negative 4, plus 0 is negative 4. Next is row 2, column 2. So that becomes 1 plus 4 is 5. As Shaq would say, get out of there. I'm going to erase that stuff. Okay, so now row 3, column 1. So this is 4 times 1. That's a 4. And then row 3, column 2. Negative 1 plus 2 is just positive 1. Oh, look, it matches up over there. I did good. Well, my 5 is... My numbers are always deformed. But anyway. Now, why is this not possible? Well, let's check the sizes. This is a 2 by 2, and this is a 3 by 2. So numbers here are not equal, right? So they're not equal, so we cannot multiply. You like to get that one on the test, right? So it's like no work. But then if you forget that concept, you end up putting some stuff down, doing some work, but it'll be the wrong work. And then you have to say, like we say in the country, God Almighty, hot almighty. Okay, so let's see. So they're both 3 by 3s, so the result would be another 3 by 3 matrix. So let's multiply. This is the first row times the first column. So I'm just doing it in my head. I hope that's okay. This is 6. Not that I have a smart head, but keep the numbers small and we're okay. If not, I have to write them all out. So this is 1 times 6 is 6. I'm just going to look at the pairs and the dot product and just say it because I keep saying this times that and then I get myself thrown off. So this is 6 minus 5, so that's a 1, then plus an 8, that's a 9. So it's a 9 for that first position. I'm going across, first row, second column. They're all times 1, so it just becomes 1 times 1, then 5 times 1, then 2 times 1. So that's just 1 plus 5 plus 2, so that's just an 8. Going across, first row, third column, so that's 3, 10 is 13, 13 plus 6 is 19. So now we come here to the second row, first column, negative 6, 0, and 4, negative 2. Second row, second column, negative 1, 0, positive 1, 0. Second row, third column, it's negative 3, 0, and a 3. That's 0. Negative 3 plus 3 is 0. Now we move to the third row, first column, 6, 12, 18. Minus 2 is 16. 16 plus 16, 32. So now this row times each of the ones, so it's just 3 plus 2 plus 4. So that's 5 and 4 is a 9. And then this position, third row, third column, 9, 4, so that's 13, plus a 12, 25. And this Dr. Isaac Green used to ask while he would be expounding on a delightful disposition at the Central Baptist Church years gone by in Pittsburgh, he would say, after a while, he would say, "Am I doing all right?" Oh boy. Okay. So let's check this one. This is they have the same sizes, 2 by 2, 2 by 2. So we do the 1 times the 2 is 2. First row times the first column. So that's a 2 plus a negative 2, 0, right? And then first row times here the second column, negative 1 plus 16, 15. And then now second row first column, 2 times 4 is 8, plus 2 times negative 1, so that's 8 minus 2, we get 6. And then second row times the second column, negative 4 and 16, so that just gives us a 12. Okay, so let's see this one. So this is 2 times 1, that's 2. And then negative 1 times 4 is negative 4, so it's 2 minus 4, negative 2. And then 2 times 2 is 4, minus 2 is a 2. Negative 1 times 1 is negative 1, plus 32, 31. Negative 1 times 2 is negative 2, plus 16, 16 minus 2, 14. Now, there had to be a reason why I put these two simple problems here in my discussion. Look at number 4 and look at number 5. I just put the matrices in reverse. Do you see that? I just changed the order of multiplication. So if I go back up, same matrices, just different order. So if you think about this, let's say for example as matrix A, and this is matrix B. So what I did was to do A times B. And A times B gave us this guy, right? 0, 15, 6, and 12. That's A times B. Now we flipped it and we did B times A. So this is B times A. So B times A gave us something different. Negative 2, 2, 31, and 14. So I think this brings us to a very good remark, and that is that normally A times B does not equal to B times A. Um, so for most cases, this is the conclusion. Matrices on a normal fashion do not commute, right? Now, and it's rare, but when they do, we reserve that to a special case that we'll talk about in the next section. Okay, let's look at this. This is pretty cool. This is a 1 by 3 times a 3 by 1. So those numbers there inside there are the same. So the resulting matrix size will be a 1 by 1. This is a matrix with just one term in it. So that's just 1 times 3 is 3, plus 2 times negative 1 is negative 2, plus 3 times 5 is 15. So we get 3 minus 2 is 1, plus 15, just get 16. Now I'm doing the same thing here with number 6 and 7. Watch. Well, I think I did. Yeah, I did. So you can think about this as being A times B. Look, that just gave us just a one tuple, you know, just a number. And then this is B times A. So this guy is a 3 by 1. This is a 1 by 3. Now those inside numbers must be the same. So the resulting matrix, right, is a 3 by 3. So basically this becomes 3 times this, you know, it's like, is this uh, this row times this column, but there's only one term in the row and there's only one term in the column. So what that does is really is you're just multiplying 3 times 1, 2, 3, and that gives us that first row. Negative 1 times 1, 2, 3 gives us the second row, and then 5 times 1, 2, 3 gives us that last row. So we just get here 3, 6, and 9, negative 1, negative 2, and negative 3, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. You know, you get to 100 and you say ready or not, here I come, and everybody's gone, right? So conclusion, I kind of said that already. Matrices normally do not commute. That's a rare case when that happens. Um, so let's talk about the trace. The trace of a square matrix, that's important. We're saying something while we're saying something, and that is that you can only take the trace of a square matrix. So I have a problem where we say, give us the trace, and the matrix is not square. Would you say the trace does not exist? The trace, very easy, the trace of a square matrix is just the sum of the entries along the main diagonal. Just add those guys up along them. We call that the main diagonal. Back in the Gauss-Jordan form, the reduced for echelon form, that's where you were trying to get the leading ones, right? Oh, I put that comment. You can only take the trace of a square matrix. Man, I tell you, I'm just cooking with some pretty good gasoline. We denote the trace by that TR and then parentheses capital A. Again, very easy to get, and you prefer doing this stuff versus trying to learn Greek, because I'm in a Greek class right now in graduate studies and seminary, and I tell you what, Greek is not math. We use all the symbols from Greek. But that's about it. But anyway, a square matrix is last semester or sometime last year? I had a student from Israel, and so he knew Hebrew. So I need that guy next semester when I take Hebrew, right? Yeah. And it's interesting because in certain abstractions in mathematics, especially in set theory, we use a lot of Hebraic symbolism to denote certain spaces, certain size of matrices. They the superset that contains everything is said to be Elif No, um, which is just the first alphabet, right, in Hebrew. But anyway, um, a square matrix is any matrix with the same number of rows as columns, denoted by uh, matrix A is the n by n. So when they say a square matrix, they're not saying A to the second power. If you say that, then oh boy, it's going to be a long semester, right? No, I'm just teasing. I made a lot of mistakes back when I was a student too, so I said and wrote some crazy things. So it's just part of life, and I'm here to, by all means, I'm gonna talk about you, but as well, I'm gonna, pat you on the back and tell you to get up and go try it again. No, I'm not gonna talk about you. Also, we only take the trace of a coefficient matrix. So let's find the trace of the following matrices. Again, you're just adding the entries along the main diagonal. So here the trace of A, just be that 6 plus 1 plus 3. So that's just 10. So nothing there. Even if we have to prove something, so here the trace of B, what is it? Well, do you see it? Does it have a trace? The trace does not exist because B, yes, I think you said it. Good. B is not, nobody's here. I'm just acting like you're here. B is not a square matrix. Right? B is a 3 by 2. It needs to be either a 3 by 3 or a 2 by 2. Okay. Here, find matrices A, X, and B that express the given system as a single matrix equation, AX equal to B, and then write out this matrix equation. What? So basically, they want us to identify matrix A, matrix X, and matrix B. No problem. So here, matrix A would be the entries for the coefficient matrix, which would be 1, 2, 0, and 1. Second column, negative 2, 1, negative 3, and 0. Third column, 3, 0, 4, and 1. Close that up. Now times the matrix X, which has entries x sub 1, x sub 2, and x sub 3. Is equal to the B column, which has entries negative 3, 0, 1, and 5. Okay. Oh, express the given linear system as a single matrix equation. Okay. This is, I guess, right out the matrix equation. I guess that's that last part. And I think they want us to write it out like this first. This is just 1, 2, 0, 1, negative 2, 1, negative 3, 0, 3, 0, 4, 1. Here we just augment the coefficient matrix. Right. So they mean the same, right? And they say the same. Just a lot of mumbo jumbo, if you ask me. Express the matrix equation as a system of linear equations. Just the reverse of what you just did. So this is just 1 times x plus 1 times y. Note the dot product, right? Note the inner product. 1 times x plus 1 times y plus 1 times z. That gives us first row x plus y plus z is equal to 2. The next row would be 2x plus 3y plus 0 times z, it's just 0, is equal to 2. And then 5x minus 3y minus 6z is equal to negative 9. That's all you were asked to do there. Now let's look at the next one. Hey, the next one we get to do some work. So here, write the system of linear equations in the form ax equal to b, and then solve. Okay. So we get a 1 at A11. You already have that. Use A11 to get zeros below. So we simply say row 1 plus row 2, and then negative 2 times row 1 plus row 3. So the first row stays the same. This is 0, adding row 1 and row 2. And then negative 2 times row 1 plus row 3. That becomes a 0. We get 4 minus 5, negative 1. Negative 6 plus 5, negative 1. Negative 30 plus 27 is negative 3. Now we move to A22. We get a 1 there. We already have that. Use that 1 to get zeros above it and below it. So remember, we got this guy, we get a 1 there, and then we get zeros below it. And then we use, once you get clean up that first column, move to the second column, and you target A22 to get a 1 there, and then now you want to try to get zeros above it and below it. So to do that, um, we'll say 2 times row 2 plus row 1, and then just add row 2 to row 3. So let's see, we're saying 2 times row 2 plus row 1, so this is a 1, 0. We get 4 plus 3, that's 7. And then 2 times 7 is 14, plus 15 is 29. Row 2 stays the same. Now we say we're just adding row 2 to row 3. So this is 0, 0, 1, and 4. Okay. So now it looks like just one more thing we need to do, and that is to say we come to this guy. We want to have a leading 1 there. We already have that. That worked out for us. And use that 1 to get zeros above it. So we'll say -7 times row 3 plus row 1, and then -2 times row 3 plus row 2. And we get this identity 1 0 0 0 1 0 0 0 1 over here. The row 3 stays the same, so I'm going to put that 4 there, and then we do the work elsewhere. -7 times the 4 is -28, plus 29 is +1, and then -2 times 4 is -8, plus 7 is -1, and we get the answer. Again, so that's something from back that you've already done in terms of solving a system using Gauss-Jordan form, and you would do that, for the rest of your life now, right? Yeah. All right. I think this is the last one. Based on the definition of the trace of a matrix, prove that if A and B are both square matrices, then the trace of A plus B is the same as the trace of A plus the trace of B. Now, there's probably a couple of ways you can work this out. The first is going to be the same all around the world. That is, you have to define these matrices. So let matrix A be of the form with the entries A1 1. I think you get the idea, to A1n, all the way down to AN1, and so on to ANN. They're saying that they're square n by n matrix. And let B have the entries B1 1, and this would be B1 2. If you keep on going over, I just didn't put that in the first one, to B1n. I guess I gotta put Bn2 all the way to B sub nn. I guess I gotta make this guy look the same as B so we can be consistent. Be like the little boy, who wants to be consistent, right? Just Just work the dang on problem. Well, that's the math version of the little kid. The kids playing baseball. One little kid got upset and took his ball. They wouldn't let him play right, and so he took his ball and went home. Tell you, adding all this stuff just makes it even more more crazier. Um, so they were fussing, about hey, are you gonna let this kid play? And the kid's walking away with the ball. You can't play baseball without a ball. And so, man, they were just standing there for about 5 minutes arguing. No baseball. And so one kid shouted out, forget about the ball. Let's get on with the game, right? So anyway, who needs all this consistency? Just work the dang on problem. Okay, let me shut up and work the problem. So now notice here that when you add the two matrices, A plus B looks like A11 plus B11. Just the corresponding entries you were adding, the first thing we talked about in this section, right? Now I'm not going to put the A12 and the B12 because just too much stuff. This is the last. I'm just going to the last terms in the corners, if that's okay. A1n plus B1n. Who wants n, right? And then this is AN1 plus BN1. And then this is ANN plus CNN. No, BNN. Okay. So now notice a simple proof begins here. Notice that the trace of A is equal to A11 plus A22 plus just adding up the entries along the main diagonal plus ANN. And the trace of B is B11 plus B12 plus and so on plus B22. Boy, I'd be so much better if I could add B22 plus and so on B sub n. What do you mean you can't add? You're a math teacher. But anyway, okay, it's the simple stuff in life that trips us up, right? Most students, statistically, end up doing poorly on exams, not due to their lack of knowledge of the particular subject matter, which that plays a factor as well too. But for the most part, the aggregated over time is just common simple mistakes that the student actually knew. It just kind of just crept up on them. So that's the trace of A is that. The trace of B is that. Now the trace of A plus B, just that matrix A plus B. Look, this guy is A11 plus B11 plus A22 plus B22 plus and so on plus ANN plus BNN. So that's what we get from this matrix here, the matrix of the sums. But if I add what I have down below, the trace of A plus the trace of B, I get A11 plus A22 plus and so on plus oh, that's not my sister Ann, that's ANN plus B11 plus B22 plus and so on plus the new news channel called BNN. Now, if I just simply add, or not add, but apply the associative property, if you will, and just associate the A11 with the B11, this guy comes out to be A11 plus B11 plus A22 plus B22 plus and so on plus ANN plus BNN, which that's the same as the trace of A plus B. So the trace of A plus the trace of B, just when you work that out, it equals the trace of the sum of the matrices. And I think that was the last problem there. Yep, I think that'll do it. Thank you.